So, welcome back. This week is 3D scanning and printing, which you might have thought from the outset was the heart of this class. The goal this week is to learn both the strengths and weaknesses of 3D printing, and we'll be seeing other ways to fabricate. And we have a dream team for the faculty for this week. So, Yogan, who you met, who did the amazing random generator, was one of the instructors. Ohad, can you introduce yourself?
I'm Ohad. I'm part of the Fab Academy since 2012. And I used to work at Stratasys, was the head of innovation, external innovation, and I had different roles over there. And now I'm doing my PhD on 3D printing multi-material for architecture scale.
Okay, and then the lead faculty this week is Adrian Bowyer, who for many of you might not need introduction. There are many claims to the original invention of 3D printing, but there's really only one claim to Adrian's role, which was he democratized 3D printing. He led turning it into an accessible thing that many people could contribute to and get access to. And so many of the printers around you directly trace back in some genealogy to Adrian, and maybe he'll share some of that. And what's less well known is he did that at heart, not simply to make things, but to make things that make things, to create self-reproducing machines. And so there's a remarkable history around what you know of Adrian in 3D printing. So you're in great hands. Take it away, Adrian.
Thank you very much, Neil. Yes, if you go to the class schedule, then click on the 3D scanning and printing link. That takes you to a webpage which has got all the notes for this class in it. It's not the lecture itself. We'll go to that in a second. But there are a great many links in here to various pieces of ancillary information, papers about various aspects of the technology that we're going to be talking about, and all that sort of thing. I'd encourage you to have a look at all that, follow the links, and discuss it with your colleagues both locally and globally. Let's go to the lecture, which is the very top link on the page there. I'll do that on my screen. So 3D scanning and printing. We're going to start with scanning and then go on to printing. And you've already heard Neil's kind introduction to the three of us. So if we look at the contents of this lecture, we'll look at scanning existing objects. How do we get existing objects into the computer so we can do something useful with them digitally? And we'll look at various scanning techniques and the shortcomings and otherwise of the technology. Then we'll get on to 3D printing, which in polite engineer speak is called additive manufacturing, but almost everybody actually calls it 3D printing. We'll look at people making things in general very briefly, and also some history. And we'll then look at why 3D print to make things rather than using some other technology. We'll then get on to the types of 3D printers that you're most likely to find in a fab lab. This list is not exclusive, but we'll just look at the most common ones. And we'll look at some design rules for using them, what they can and can't do, and how you set about using them. We'll look at some tricks and techniques. And we'll also look at other 3D printing technologies, which are, though important, less likely for you to encounter. And then finally, of course, we'll get on to the assignment for this week. Okay, let's start with scanning then. A bit of history. The oldest way to do scanning digitally was to use a thing called a coordinate measuring machine. This is a great bulky Cartesian robot made out of artificial granite with air bearings. And it had a physical touch probe, which I've illustrated on the right. Now, these machines did two things. One is that they checked the dimensions of objects that had been manufactured. So you could use the touch probe to measure the internal diameter of a hole, for example. But they could also be used to scan an entire object by repeatedly touching it all over its surface. And the reason I've introduced this is not so much that you'll be using it, but because the touch probe itself is rather interesting. It illustrates a number of neat technical ideas. It's illustrated, as I say, on there on the right, and it consists of 3 rods which rest on 6 balls. And you wire those balls in series such that the 3 rods make a connection between each pair of balls. And then almost any way in which the probe touches something, the electrical contact, the electrical circuit's broken, and you can detect that very easily. And there are 2 reasons for putting this up. One is because it illustrates the fact that if you want to use a physical touch to detect something, it's much better to break a contact with that touch than to make it. That produces a much more accurate and repeatable result. The second reason is that it's very easy to print something, and we'll get on to 3D printing later, that does this job. And so it's a generally useful principle. If you want to make something that touches something and tells you when you got there, this is a good way of doing it. But let's now look at scanning and objects in general, and forgetting for the moment how we achieve this. If we've got an object like the object on the left there, when we scanned it somehow or other, we're going to end up not with the object itself represented inside the computer, but a cloud of points as illustrated on the right. You're basically going to have a whole list, thousands and thousands almost certainly, of XYZ coordinates in space that, things have gone well, will be points on the surface of the object. And we're going to have to turn that into something useful, because we couldn't, for example, take that information and, let's say, 3D print it directly. We'd have to process it before we got to the point of being able to make it, make a copy of the original object. So we've got to take that point cloud and turn it into something that's more usable. And here's a point cloud representing an elephant on the left. And what we need to do is to take that inside the computer and turn it into a triangulation that covers the surface of the elephant that we originally got the point cloud from. Now, this is turning the points into a pattern of polygons. Those polygons are almost always, in fact, triangles. Triangles are the most useful shape for this because they're always guaranteed to be flat. There's no ambiguity about their surface. As soon as you've got 4 points forming a quadrilateral, those 4 points won't necessarily lie in a plane, and you're not quite sure which diagonal is which and what the surface is that they represent. So triangles, when we say polygons. And you've got another problem to solve if you use the probe technique, and I'll briefly mention it here, which of course is that the thing you measured when you put the probe against the surface was not the surface, but the center of the probe. And so it's actually offset from the surface a little way, and you've got to do something about that. And I mentioned this here because it introduces an idea that we're going to get to a little bit later on, which is the idea of a Minkowski sum. What a Minkowski sum is, and I've illustrated actually a Minkowski difference here, is the way to add 2 shapes such that it solves precisely this problem. If you've got a shape which is the result of touching something with a probe, which is a sphere, and you want to get back to the original object, then what you want to do is to subtract the sphere from the thing you've got to end up with the original object you want. Now, don't worry too much about that at this stage. We're going to get into more detail about that later on. But forget about touching. What we really want is a system that allows us to measure and scan objects which doesn't require us to touch them at all, so that we can use the same technique that we use when we use our eyes to look at a 3-dimensional scene. And almost all methods of doing this rely on some variation on the idea of binocular stereo vision. Stereo, what we're doing is trying to reconstruct a solid, in the case of vision, inside our own heads, or in the case of with some sort of scanner inside the computer. And if we look at the way that stereo vision works, most people know this. What we're doing when we look at something with our 2 eyes is that our brain knows the angle between our eyes, which we need to move them to fix on a given point on the left-hand diagram there. And that angle tells us how far away the point is by straightforward triangulation. But of course, we don't just see one point in 3 dimensions, we see a whole scene in 3 dimensions. So if we look at some other point, the little square there, that will produce an image on our 2 retinas in slightly different positions, the left retina and the right retina. And we can use that information to figure out where the little square is, as well as the circle, which we originally focused on. Now, we need to do that quickly. The reason being that it's no use knowing how far away the tiger is 5 seconds after it's eaten you. So what we need to do is to have 2 eyes there. But if we're going to scan an object, we can sacrifice the need to do things very fast and simplify the scanning technology so that we only have one camera, and we perhaps move that camera around, or we move the object around. So on the right, we can see a system with a camera and an object we want to scan on a turntable. If we rotate the turntable a little bit, that's the equivalent of having two eyes. And of course, we can continue that process and do a complete 360-degree rotation. And then we'll have a whole series, a movie of images of the object. And with a bit of luck, we'll be able to reconstruct what it's like in 3 dimensions in pretty much the same way as our eyes work. But there are problems, and we have to solve those. So let's look at something which goes way back to the Victorian era, which is taking stereo images as photographs and then trying to figure out what it is that we're looking at. Here are a couple of pictures of the same pair of roses. And taking 2 pictures is pretty easy, as I just indicated. We either have 2 cameras, or much more likely, we simply have one camera and move it a little bit to the right to take the right-hand image. So gathering images, an easy part of the scanning tool chain. The next bit is difficult. What we need to do, and something that you do instinctively, when you look at a 3-dimensional scene, is to solve the problem that's called point correspondence. Point correspondence is figuring out that the corner of the leaf that I've labeled with a little red dot on the left-hand image, sorry, corner of the petal, I should say, not leaf, the corner of the petal with the red dot is the same corner with the red dot on the right-hand image. And as I say, your brain has had, well, it's had 3.5 billion years of evolution to figure that problem out. But getting a computer to solve that problem is difficult, and we'll look at how we can go about that in a little while. Now, that's a genuine stereo pair. So if you take that image off the slide when you're looking at it yourself, and you reduce it down so it's the gap between the 2 pictures is a little bit smaller than the gap between your actual eyes, put a couple of magnifying glasses in front of your eyes, suddenly it'll all jump into 3 dimensions. And what's more, you'll see that the little red dot is in the right point in 3-dimensional space for the corner of that petal. So this is a hard problem we have to solve as the second stage in our scan. The third problem is now fairly easy. Once we've solved the second problem, that's to make an entire cloud of points. If we can solve the correspondence problem, then we can obviously repeatedly solve it and produce a whole series of points all over the object that we're scanning. And then the final problem that we have to solve is taking that point cloud, as I mentioned before with the elephant, and turning it into some sort of more structured representation of the object that we scanned. In other words, we have to triangulate it. And this, once again, is a hard problem. It's fairly areas which are broadly flat, but where we've got lots of detail, it suddenly gets very difficult very quickly. So we've got these 4 stages to the process, 2 of them easy and 2 of them hard. Okay, let's look at the point correspondence problem to start off with. We can simplify that by forgetting about the fact that we might have 2 images, just have 1 image, but structure the light which is illuminating the object that we wish to scan. So we might have a camera that's producing the picture that you can see, and then instead of a second camera to produce the second image, or instead of moving the camera to produce the second image, what we might do is to shine a laser into our scene, which will produce a bright dot on the object. And we've now got a piece of geometry which we can very straightforwardly analyze. The computer can spot the bright dot on the image with no difficulty whatsoever. And once we've got that bright dot, because we know where the laser is, we know which way it's pointing, we know where the camera is, we know which way the camera is pointing, we've got the 3-dimensional coordinates of the dot. And there are a whole series of different approaches to this problem that basically use the same idea, which is that we have a camera and we have some form of structured light, the simplest structure being a sharp, fine beam of light, such as a laser produces, or we might have a sheet of light, such as a sheet of light that's produced by a supermarket scanner to scan a barcode. All sorts of ways that we can structure light in order to make the problem of figuring out where that light hits the object we want to scan actually is in space. So this is one approach to the point correspondence problem. It sort of short circuits the difficulty of being able to recognize that the corner of a petal in one image is the same thing as the corner of the same petal in a second image. Why is triangulating and meshing a scan difficult? Well, if we start with forget about 3 dimensions at the moment, let's look in 2 dimensions. Suppose we simple object, the 2 squares you can see top left there. Now, if we were to scan those, we'd get a series of points, not in space this time, but in 2 dimensions, such as the red dots you can see in the middle of the slide there. Now, I think you can see that we don't have enough information there unambiguously to reproduce the original object on the left. If we went about trying to reproduce that object, we might well end up with the object bottom right, because we don't know what's going on in the corners, because we didn't quite happen to hit those corners with our scan. We don't know what's going on at the join between the two objects, because once again, the scan is a little bit ambiguous there. And so we've got insufficient information to reconstruct the surface of the object as a pattern. Well, in this case of lines, in 3 dimensions, it would be a pattern of triangles. So obvious solution to this is to gather more points, and that will reduce the ambiguity, but the ambiguity is always going to remain in some circumstances. And this is an inherent problem with scanning in this sort of way. It's not one we can escape. We can merely minimize it. Okay, so how do we go about actually doing a reconstruction? This is a famous example object. It's called the Stanford Bunny. If we've got a series of points on its surface, then one of the best ways of doing the reconstruction of that surface, that is to say, producing a series of triangles that represent it, is called Poisson surface reconstruction. There's a link to the paper on this in the notes. But you'll notice on the left, the points which we're using to do the reconstruction have suddenly grown a series of hairs. The bunny has got its fur back. The reason for that is that for this technique to work, we don't just need the points on the surface, we also need the normal vector to the surface. That is to say, we need a line pointing out from the surface at right angles to the surface to use this method of reconstruction. Unfortunately, let me be clear, fortunately, there are ways to do this, and it's fairly straightforward where the surface is reasonably flat. You take small groups of points and use things like principal component analysis in order to work out what the normal vectors roughly ought to be. So this is a pretty much solved problem. If you've got enough points, they're close enough together, and you can solve the much simpler problem of figuring out what the lines to the surface at right angles are, what the normals to the surface are. So back to scanners. Here's an example of a scanner that was made in Fab Lab in Aachen. It's called FabScan Pi because it works with the Raspberry Pi, and indeed you can see the connections to a Raspberry Pi bottom right in the laser cut box there. And it consists of a turntable which rotates an object, and you can scan the object with the optics that's arranged on the left there. And here's another similar setup. This is actually the scanner in the room next to me right now. This is my Creality Ferret Pro 3D scanner. The way this works is with structured light. It does actually have 2 cameras within it, and it projects a pattern of infrared light onto the object to be scanned, which is rotated on the turntable that you can see connected by the white wire. The object rotates, the pattern of infrared light is projected on it, the cameras pick that pattern up and work out the surface of the object. One of the nice things you can do here is that because you've got the cameras, you can turn the infrared light off and you can see what color the object is, where the infrared light used to hit it when the infrared light was on. And that allows you not only to scan the object, but also to have a 3-dimensional representation of it in color, because the cameras can pick that up when they're not doing the actual scanning with light. So this is a fairly straightforward machine. It costs about, I think, about $300. I can't quite remember what it cost when I bought it, but something like that. So they're not horrendously expensive. And I think quite a few Fab Labs have got exactly this device, which plugs into your laptop and allows you to scan an object and produce a 3-dimensional representation of it inside the computer as a triangulation, which you can then read into a CAD system reasonably painlessly. So that is a solved problem, albeit requiring some quite intensive computational work going on in the background. Okay, well, that's scanning, but most of this lecture is going to be about 3D printing. So let's move on to that now.
Adrian, before you leave this, just a note, scanning is increasingly important for augmented reality. So a lot of commercial effort is going into it for cell phones, and increasingly the way it's done, those are doing is time of flight.
Yeah.
And input devices will cover time of flight measurement, which is incredibly difficult. Light travels a foot in a nanosecond. And so you need to measure picoseconds, milli, micro, nano, pico. But increasingly, there are cameras where each pixel can measure picosecond timing. And so that used to be very specialized. That's now becoming more accessible for 3D scanning. The biggest limitation on it is the vendors developing it keep getting bought by the chip and cell phone companies. And so it keeps rearranging, but that's beginning to take over for 3D scanning.
Yes, indeed. And you can get such devices which project a whole pattern, an 8x8 pattern of timed beams, which will come back and give you an entire surface map of the object that you're looking at. The typical sort of ranges that you can scan over with those is from, say, perhaps 200 millimeters out to 4 meters, something like that. So,
but again, the latest generation iPhones have whole imagers actually doing this picosecond timing. So it's going to rapidly displace how we scan.
Yeah, you're right. Yeah, excuse me. Okay, 3D printing. 3D printing is a way of making things. Let's look at making things. There are 4 fundamental ways humans make shape in solid objects right since prehistory. Obviously, we can cut things. We could cut leather. We can cut cloth that we've made. Or we can chisel material away. We can take a block of material and subtract material from it to leave the shape that we want. We can take material that's deformable, for example, viscous but molten glass, and deform it into the shape that we want. Or we can add material to make up the shape we want, for example, as we might do with rolled out sausages of clay to make a pot. And we're going to look at 2 of these in a little bit more detail in a while, but let's just go back and look at the history of 3D printing itself for the moment, and then we'll look at 2 of those 4 methods and compare them, one of which will be 3D printing. So 3D printing goes back a surprisingly long way. This is almost 100 years old. It dates back to the 1930s. Many of you will have seen that these days people are 3D printing buildings by having a large Cartesian robot that moves a deposition head about to put concrete down. Well, here is William Herschel's 3D printer for producing buildings. And we've got a rather speeded up movie on the right-hand side there. These buildings had to be cylindrical. It was 100 years ago. And what's more, the material had to be put in by hand, but you could stop it and form a window, as you've just seen. Basically, 2 people had to continually be pouring cement that they've mixed up into the right head of this machine in order to construct these circular buildings. And this, as far as I'm aware, is the first thing that could really be called a 3D printer in the modern sense. And as I say, it was just about before the start of the Second World War. Moving on in history a little bit, this guy on the left is a guy called David Jones, and he used to write a sort of scientific joke column in the New Scientist magazine. And back in 1974, just over 50 years ago, he came up with, I guess, what we call the first modern 3D printer. And this was also at the same time being patented by someone else, a guy called Wynne Kelly Swainson, who didn't know about Jones, and Jones didn't know about him. But the patent turned into a proposal for a 3D printing machine, which you can see illustrated on the right. The idea is that you have some photoresist material, a liquid monomer that polymerizes when light hits it, and you shine 2 lasers into it, and at the intersection of the beams, the polymer is formed from the monomer because the polymer sets in the presence of those sufficiently intense light, the light from those 2 lasers. Now, in the notes, you'll find a link to 2-photon 3D printing. And this idea is essentially that. And it dates right back to this idea, Jones, who wrote it as a joke because he didn't think it would actually be possible to do back in 1974. Moving on to the first machines that actually appeared on the market and that you could go out and buy, albeit with a great deal of money. This is the first commercially available 3D printing system, which was invented by Charles Hull. This is a system called stereolithography, which we'll get to a little bit later on. And there he is with one of the machines, not the very first machine, but one of the machines that works with this technology. A little bit later, Scott Crump, illustrated on the right there with a cup of coffee, came up with a different way of producing 3D prints, which he called FDM. He did it by being requested, I'm told this by Ohad, he did it by being requested by his child to produce a model toy, and they couldn't get to the shops. So he made the model with a glue gun. He literally used the glue gun to scribble in 3 dimensions to make a plastic toy for his child. And then realized that this might form the basis of a production process. We'll be talking about this in considerable detail in a minute. And then, if I may mention my own name, this is the RepRap project. This is taking FDM 3D printers. The one on the left was made in fact, a Stratasys machine, the Scott Crump machine that you just saw me talk about. And the machine on the right was made by Vic Oliver and me in using the machine on the left. So all the plastic bits in the machine on the right were made in the machine on the left. So we were trying to make a self-replicating 3D printer. And you can almost certainly see from my image that I'm horribly old. I can tell you that it doesn't feel any older than it's possible to feel until you find your own object in the Science Museum in London. There it is on the right. And I'm afraid that my own creations are now museum pieces, and there it is. That's the very first machine. That's also the one in the photograph on the left. Anyway, so that's 3D printer printing the parts for another 3D printer. Okay, why 3D print? Let's look at some reasons. The first obvious one is that it makes lots of interesting, useful machinery and other stuff, sculptures and so on. So on the left, we have some pictures of the Open Fletcher microscope. That's an open source 3D printed microscope. On the right is actually something from a Fab lab. It's a Pico CNC printed circuit mill. It's for milling printed circuits, and that's a device that's largely 3D printed. Now, going back to people making things, you remember we had this idea of subtractive manufacturing, where we take a block and we cut it away, or we have additive manufacturing, where we add material on. Now, the modern interpretation of this, of course, is to add a computer to move a machine around to do both of these processes. So on the left, we have computer numerically controlled milling, which is basically a computer moves an electric drill around in space, and wherever the drill bit spins, it removes material. And we also have 3D printers, which is the additive computer-controlled method of manufacturing. What we do is we scribble on that blue plate there with molten plastic, then we move the plate down a little bit and scribble the next layer and scribble the next layer, and so on. Let's contrast these, as these are two principal ways of making three-dimensional objects, and see how they compare with one another. And we'll start with the advantages of 3D printing, but we'll get onto the disadvantages in a little while. So why 3D print? Well, the first and most obvious reason is big forces versus small forces. The sorts of forces you get with CNC milling are typically something like 500 newtons, perhaps. You need very rigid machinery with big castings in order to hold everything in the right place to resist those forces. In contrast, when you're 3D printing something, the typical sort of forces you might be dealing with, something like 5 newtons, 100 times smaller. Admittedly, the process is slower, but nonetheless, the forces involved are comparatively negligible compared to those with milling, used with milling. Now, this is a bit of a subtle point, but it's an important one. If we want to make a complicated shape in a CNC mill, we want to cut the complicated shape out of a block, we're going to need what's called a 5-axis CNC mill. This is a mill which is capable of moving 5 independent ways. It can obviously move in X and Y and Z, as you might expect, but it also has 2 rotations, which are illustrated at the bottom on the left there with the yellow arrows. And it needs all that in order to be able to move the cutting tool around in such a way that it can cut out that shape. So we've got a 5-dimensional problem to solve if we have to have the computer figure out how to cut the shape out. In contrast with 3D printing, we're always building in flat layers, which means that the 3D printer really only has to worry about 2 dimensions and calculate things in 2 dimensions in order to solve the problem of manufacturing the object that we want. Now, if you've ever written any software for dealing with geometric problems, one of the things you will have found is that as the number of dimensions increases, the difficulty of the software and the problems that you encounter in making it work get it gets an awful lot worse as the number of dimensions increases. So controlling a 5-axis CNC mill is simply a much more difficult computational problem than controlling a 3D printer, which only has to effectively at any one time be working in 2 dimensions. Another advantage we got with 3D printing is that we know that everywhere above the plane in which we're printing is going to be free of any obstructions. So we can move the printer around freely in all of that space. You don't have that freedom with CNC milling. As you're moving the cutting tool around, you want to make sure not only that it's cutting the bit that you want, but it's not colliding with something that you want to keep. So like the rest of the machine, let alone the thing you're making. So there are problems with milling that you don't get with 3D printing because of this difference in the number of dimensions that the computer has to deal with. Okay, even more fundamentally, there are things that milling can't make and 3D printing can. Here's a simple whistle, top left. If we make the image transparent, you can see that it's got a little P in it, which rattles around in it to make a warbling sound when the whistle's blown. Now, a CNC mill can't make that shape. It can't get to the inside in order to cut round the little P, and it can't cut the cavity because there's simply no way that it can access. On the other hand, if we 3D print this in layers, and there's an illustration 1, 2, 3, 4 of the printing at different stages, we always have access because of the reason that I mentioned when we were looking at the last slide. So we can print the entire object, but we couldn't mill it. The little P is still attached to the base of the print there when it comes off the machine, but all we do is reach in with a small screwdriver, flip it away from the base, whereupon it rattles around the inside and makes the right noise. The top of the whistle that you can see there, the dark red color in the final picture, that's unsupported when it's printed, and we'll talk about that in a minute as well. Okay, another thing with 3D printing is that complexity is almost free. The more complicated something that you're milling, the more difficult that milling operation is, and the more time it will almost certainly take. No matter how complicated something is, you can almost certainly 3D print it in pretty much the same time as it takes to print something, I beg your pardon, that's quite simple in shape. Okay, here's another example of complexity. We've got some Additive footwear components on the left. We've got some printed masks on the right. And as you can see, simplicity is not the word that comes to mind when you look at either of these pictures, but 3D printing makes making this sort of thing pretty straightforward. Okay, another advantage. Milling creates waste. When you're cutting material, you get swarf, and that has to be disposed of and recycled. 3D printing is a near net shape process. We occasionally have to have extra material, which we're going to throw away, as we'll see, but nonetheless, it's a much neater and tidier process with less waste material than milling. Okay, another thing we can do with 3D printing is to make functional objects in a single shot, which is virtually impossible to do with CNC milling, and we'll have a look at this in a little while as well. In other words, the objects on the right were made in a 3D printer in one go. They weren't made in pieces and then subsequently assembled. Okay, now that's all the advantages. Let's look at how it goes wrong. Here we've got some failures. On the left, what's called bird's nesting. If our 3D printer is depositing plastic, that doesn't always stick down as it's supposed to, and you can end up with a sort of wild pink haircut as in the middle on the left there. Clearly you didn't want that, and that's been a waste of time and material. Alternatively, things can stick too well, illustrated by the picture in the middle there. The object that was being printed is actually stuck to the right head of the machine and is detached from where it was supposed to be retained, and so that's another failed print. And what's more, we've got more polymer extruding at the top there, making a mess of the entire machine. SLA printing can also fail. We find that objects distort when they're not properly supported, and we'll get into that later on as well. So it's not a perfect process. Okay, let's have a look at a couple of the machines that we're likely to find in Fab Labs. The first one, the one on the left, technology, the Scott Crump technology called Fused Deposition Modeling, FDM. Now that's a trademark term, so to replace that, I came up with the phrase fused filament fabrication and basically open source that phrase. And if you look up 3D printing on Wikipedia, you'll find that FDM is called FFF on Wikipedia because it's a free term. FDM is trademark. The second type of machine is stereolithography. The full title of this is Mass Stereolithography Apparatus, MSLA, but almost everybody calls this stereolithography and leaves the M off the front and calls it SLA. So you'll find this called stereolithography or SLA. Okay, I'm going to start by looking at FFF 3D printing. Most people know how this works, and it's illustrated on the right there in that little movie. We're extruding molten plastic, and it's sticking down to the plastic we've already laid down to form the next layer. And we have a spool of filament illustrated on the left that's forced down through a heated nozzle. It melts, comes out from the bottom of the nozzle, and we build it onto the object. We have a build platform that gradually descends, or the head gradually ascends, and we build the object up in this way. As I mentioned earlier, it's basically a computer-controlled hot glue gun. Now, this is a slow process. So on the left, we have an illustration of a standard test object, which is called 3D Benchy, and we'll return to that in a minute. But if we try and make something like this really fast, for example, on the right there is an attempt to make this in 3 minutes, and you can see that the result was not the highest quality. So it's a comparatively slow process to make things. That's the first disadvantage of it. Another thing we have to be careful of is the emissions from this technology. There's a link to the paper in the notes for this, from which we're taking this diagram. And so what we've got in the left-hand diagram there is emission of ultrafine particles by various 3D printing machines using various materials. The first thing to notice on the left-hand axis is that it's a log scale. So we've got an enormous range of particles emitted over time represented by that left-hand axis. Now, on the right hand of the diagram, we've got a polymer called PLA, which is short for polylactic acid. And this is pretty benign. The particulate emissions from it are not that great. We can do it in the open air, and everything will be pretty much fine. PLA, in fact, is a polymer of a sugar, and you'll find that when it gets too hot, it actually smells of caramel. So it's pretty much the same sort of pollution that you might get from cooking operations in some circumstances. But as we move to the left there, the particulate emissions get greater and greater, as also do the emission of volatile organic compounds, which are sometimes not very benign, sometimes malign. And we have to watch out for both of those. And so the further with the left we get, the more likely we are to want to have our machine enclosed in a casing and to ventilate it through an activated carbon filter in order to take the nasty stuff out and also the particulates. And on the right there's an example of a certificate of compliance. There's a certification scheme for machines that ensures that they correspond with certain standards as far as these potentially damaging materials and their emission is concerned. Okay, now if you go to websites that sell filament, you'll find all sorts of, I don't read all the numbers on this slide, they're not that important, you can check them out later. You've got all sorts of materials and there are all sorts of mechanical properties that you'll find, and you can select the material that does what you want. Notice though in the second column there, we've got a flexible plastic, and we can print with flexible plastic in these machines, and we'll come back to that later on as well. This is the page of Simplify 3D that sell filament. And once we got our filament from our supplier, we had to take care of it. PLA in particular is hygroscopic, which is to say it absorbs water from the atmosphere. We want to put it in a container and keep the air in that container dry to keep it in good condition. So you want some sort of hermetically sealed container into which you put some of these silica gel pouches that keep the air in there dry. PLA and PETG are the two most likely polymers that you're going to be encountering. PLA is plant-based. It's got a fairly low glass transition, so it won't work at very high temperatures, but it is very easy to print, works very well. PETG works at slightly higher temperatures, and also has better UV resistance. Having said that, PLA often has titanium dioxide put in as a filler, and that basically makes it pretty UV resistant as well. Titanium dioxide being the material they put in sunscreen, which you wipe on yourself when you go and sit on the beach. Okay, now let's look at some design rules for 3D printing. If you want to make the object top right, you're actually going to end up making the object top left. The reason being that as the machine is building that up in layers, in an FFF 3D printer this is, it can't support the overhang. And so what we have to do is to build up some extra material under that overhang, and we throw that material away when the print is finished, or ideally recycle it. And the print of the material that does the support, called support material, that material is printed in such a way that it very easily detaches, and it's very friable, it crumbles very easily, so we can detach it from our print very straightforwardly. At the bottom you can see an illustration of a solution to the same problem, which is slightly more subtle. It's a brachiating tree-like structure that uses less support material to achieve the same result. Okay, now I say we need to support things that overhang. In fact, we don't, as long as the overhang is not too bad. And here's an experiment with a whole series of different angles of overhang. You can see at the extreme right-hand end, we've got a very poor print, particularly on the underside of the overhang. But down to about 40, 30 degrees or so, the print is pretty good. So this technology can allow us to do a certain amount of overhang as long as it doesn't get too flat an angle. And that's something that's quite advantageous. Now there's another thing that we can do as far as printing in thin air is concerned, and that's called bridging. If we put a support at either end when we're printing a bridge with nothing underneath it, then because the polymer, when it's molten, is a non-Newtonian viscous fluid, as long as we drag it quickly enough between the one end and the other, then it will stay reasonably well up in the air as it solidifies without dropping too much, and we can build a bridge without any support underneath it. Now there's obviously a limit to this. You probably couldn't build a bridge that was 200 millimeters long in a conventional printer. It would sag in the middle, but as long as the bridge isn't too long, we can do that without support material. And this brings us to a rather clever design of FFF 3D printer that was come about by considering a number of these things that we've just been discussing, in particular the ability to print at an angle without needing support. And this is a printer that consists of a belt, a conveyor belt, and you print on the conveyor belt. And the movement of the conveyor belt is like the movement of the print bed in a 3D printer that's got a Cartesian coordinate system. So if you look at the machine on the left, that's made by Creality. The belt is the belt there, and you can see it's printing a series of chess pieces. And the print is actually being carried out by a print head that moves at 40 degrees to the horizontal, not vertically. And I'll come to that in a second. But the first and obvious advantage of this machine is it'll print continuously. We can use it in mass production, put a bucket under the end of it, and all our objects that we're printing will fall off into the bucket, and we can keep doing that all day long without any attention from a human being. The second advantage it has is that if you look at the shape in the top in the middle, this cube, which has got its faces and interior missing, you might just be able to print that using the bridging technique that I just mentioned. But if you print that shape in one of these machines, it turns out that the 45-degree overhang rule, which we can get away with, allows us actually to print it without any support material in any scale that the machine is capable of. And this is extremely convenient. It allows us to get rid of the whole support material problem. Finally, and fairly obviously but interestingly, we can extend the belt, the belt on which the print is being done, and produce a print of any length that we like. We can make a 6-meter long beam if we want in one of these machines, and that's obviously advantageous for many problems as well. Okay, back to the design rules for this type of technology. Let's suppose we design a central cylindrical shaft, top left, and we put a series of square objects around it with a hole through the middle. And let's suppose we set different clearances between the two. So perhaps at the left-hand end, we've got a 1 millimeter clearance down to a 0.1 millimeter clearance at the right-hand end. Now, if we feed this into our 3D printer, it will obviously have to have some support material, which is the top there. You can see at the very topmost image. We take that support material away, we'll discover that some of the little blocks are free to rotate, and we've actually effectively made a mechanism. Some of them will be too tightly constrained by the small clearance between them and the rod that they won't move anymore. And so we can make a mechanism in one shot inside the machine, as mentioned previously. There's the same experiment with a different pattern of support material at the bottom there. On the right is a scissor screw jack that actually was made by my daughter. Now, the interesting thing about this is that it is made in one shot. The knurled knob you can see there connects to a screw thread, which drives a nut, which works the scissor mechanism, and the whole thing can be wound up and down by turning that knob. It comes off the 3D printer, as shown on the bottom right, in that vertical configuration, as a single print. Doesn't need any support material indeed. And when you turn the knob, you hear it go crack, and then suddenly the whole thing turns into a mechanism, and you've got a complete machine printed in one go. Okay, another aspect to this technology is anisotropy. We're printing in layers. If you make this L shape, you'll find that the horizontal bit of the L is extremely strong. You probably wouldn't be able to break it with your fingers, but you probably will be able to snap the vertical, because the welding between the layers is not as strong as the plastic solidifying inner layer. So you get an anisotropic mechanical properties. Another thing is dimensional accuracy. Here's a block printed with a 20mm block with a 10mm hole. You'll discover that when you make holes in objects and print them, the holes usually come out a little bit undersized, and you often have to allow for that. The exterior dimensions are normally not too bad, but the interior dimensions sometimes can, as I say, be a bit undersized. Similarly, surface finish. We're printing in layers, you'd expect to get steps, and so indeed we do, as you can see illustrated with this printed sphere and printed spherical cavity. That may or may not be a problem. Infill. When we're printing something, on the left there, we printed an object where it's completely solid, but normally that's not done. The reason is that it doesn't actually make the object that much stronger to make it solid. If we put some sort of honeycomb in the interior, we end up with something that's almost as good, but it's much quicker to print because we left material out and it uses less material. So we got different percentages of infill here, from 100%, which is rarely done, through 50, 15, down to 0, where there's no infill at all, and we're relying on bridging to do the top surface of the object when it gets there. And there are various infill patterns that you can select when you use one of these machines. They usually have honeycombs or patterns of internal cube voids, that sort of thing. This is a rather special pattern we've got here. This is called free flow infill. It has the characteristic that were you to pour a liquid into it, it would flow everywhere without being constrained in one chamber. In other words, the air inside is fully connected with all the other air inside. And we can take advantage of this to do another trick. Top illustration is the foot of the heat pump that heats my house. It needed a support underneath it. If I just printed that, it wouldn't have been strong enough. But if I add a couple of things to my design, in analogy with casting a hot riser and a cold riser, and I then print that object, and I cut the tops of the risers off, so I got the infill that's in the interior. If it's that free flow infill, I can mix up some resin, pour it down the hot riser, wait till it sets, cut the risers off, and now I've got a 3D print that was made in an FFF 3D printer, but which is filled with solid resin. And that is, of course, much, much stronger, and indeed strong enough to support the weight of a heat pump. Bed leveling. When you've got one of these machines, the bed will find it is almost level, but it's never perfectly level. And when the machine is moving about to print, it has to allow for the fact that the bed is not perfectly level. Almost all of these machines are capable of detecting when the nozzle touches the bed, and they use this to map out the bed before they start. So you touch the nozzle onto the bed repeatedly in a square pattern all over the bed, and you end up with a map of the bed, as illustrated on the right there. That map has got the vertical dimension very much exaggerated. It probably represents only about 0.2 of a millimeter or so in difference between the top and the bottom. The machine can then use that map when it's actually doing the print in order to move the head very slightly up and down to get a consistent distance between the nozzle and the bed. This is very important so that the very first layer of the print adheres strongly to the bed and doesn't detach itself. And as I say, this is a trick that almost all modern FFF 3D printers can do. But it leads us to another idea, back to that coordinate measuring machine, you remember, with its spherical probe. We can actually turn a 3D printer into a coordinate measuring machine. If you hold a ball bearing under the nozzle and extrude a little bit of plastic and let the whole thing go cold, the plastic will hold the ball bearing. And because the printer knows when its nozzle touches something, you can use the printer to move around in space and to digitize a three-dimensional object. The result won't be very good, but it will be adequate for some purposes, and it's quite a neat sort of application of the technology. Okay, another aspect of 3D printing is that you sometimes, in addition to support material, need to add other material. And this normally goes under three titles: skirt, brim, and raft. A skirt is a run of material around the outside of the object that you're going to print. All this does is to clear the throat, as it were, of the printing nozzle, make sure that the filament is flowing properly before you start the print. It's just a way of making sure everything's working. If you've got a small surface area in contact with the build plate, then sometimes it doesn't stick down well enough and the print will become detached, as we saw in the problem prints slide of quite a while back. So what you can do is you can add some brim. This basically increases the area at the very bottom of the print and stops it from detaching from the bed. And finally, we can have a raft, which is where we lay down some material underneath the print before the print even starts, which essentially solves the same problem as the brim solves, plus also allowing us perhaps to level things up a little bit before the print gets started. Okay, another trick we can do is we can stop the print partway through and insert things in order to produce more active objects. So here's a rectangular block that I wanted a pattern of high intensity magnets in. I left cavities for those magnets in the design, paused the print when it got to the top of those cavities, put the magnets in by hand, then resumed the print. The print carried on printing over the top of the magnets, and I ended up with a rectangular block with a pattern of magnets embedded in it that I wanted. And you can use this for other things as well, as we shall see in a minute. Okay, another thing you can do is to mess about with the way the infill works. So, for example, you can take a random pattern of very fine cylinders and subtract them from an object. Now, this seems kind of crazy, but this illustrated top right there, that object has had a series of random cylinders that are subtracted from it. The effect of this is a little bit like making the object out of fiberglass. And the reason for that is because the printer will print those cylinders in such a way that they have a continuous surface as opposed to the infill, which has the effect of reinforcing the print. But we can be a bit cleverer than that. So if we take a simple beam, left there, distortion of it. If we take that simple beam in a CAD system like, for example, FreeCAD's got a built-in finite element modeler, and we load the beam in FreeCAD before we've even manufactured it, we can figure out where the high stresses are if it's clamped at the left and loaded at the right. Unsurprisingly, the high stresses will be at the top and the bottom of the left-hand end of the beam. We can then subtract some fine cylinders interior to the beam at that point and print it with those cylinders in, and the machine will lay down extra material just where those cylinders are. And if we then do the test on the beam with and without those cylinders, as illustrated in the middle there by hanging weights on it, on the right you can see the results. We've got deflection up the y-axis and the load in newtons on the x-axis. The blue curve is the unreinforced beam and the red curve is the stiffer reinforced beam. So we can, as I say, put internal structure in a print which you'll never see, but which nonetheless achieves different mechanical properties. With fused filament fabrication, we can have more than one material. This allows us to do colors, so we can have multicolor prints. There's our 3D benchy again. We can combine hard plastic and rubber-like plastic to make objects which are rigid in some places and bend in others. You can get filament which is electrically conducting, so you can build a print which has got embedded conductors within it. a slight warning here. If you're used to copper, which has got a resistivity of 17 times 10 to the minus 7 ohm centimeters, the conducting filament is about 10 million times worse. So it's a conductor, and with a fairly chunky piece of it, you can illuminate an LED, but it's not like working with a metal as far as electrical conductivity is concerned. Another thing you can do with a multi-material printer is to have the support materials soluble. So here we've got on the right, we've got a print which we want, which is the black part, but the white material is soluble. And if we print the two together, the soluble material acts as a support. We then drop the whole thing into water and the soluble material is dissolved away, and we end up with the print that we want. The usual soluble material uses PVA, polyvinyl alcohol. That's water soluble, but there are other ones that, for example, will dissolve in sodium hydroxide and other slightly less benign things than water. Okay, one of the things we've got to do with our 3D print when we've got the object that we want to print is to turn it into layers. And the object is represented by an STL file, and we'll talk about that in a minute. But what we do is we take the object and we cut slices through it inside the computer to work out what each layer is going to print like. And what this does is to generate a G-code file to control the printer. G-code is a standard code for controlling all sorts of numerically controlled machines, not just 3D printers, CNC mills, CNC lathes, all sorts of things. They're all controlled by G-codes. So if we briefly look at the output of this slicing process, here we've got 3 G-codes down there. Now, you can take these files, they're text files, and you can edit them by hand if you're feeling brave. But there is the danger that you might move the machine to the wrong place and cause it to collide with itself. But the G-codes are pretty straightforward. For example, a G1 just says move somewhere. So what the top command there is saying move to X0, Y0, Z3. In other words, the origin of coordinates in X and Y and 3 millimeters high in Z. And the feed rate is in millimeters per minute, so 2.4 meters per minute. We then want to move closer to the machine's bed, 0.2 high at a slower rate. And then we might move and start doing some printing. So what the third line is doing is move from the point X equals 0, which is where we were, to X equals 30. But it's also extruding 10 millimeters of filament while it did so. And the G-codes just treat the extrusion as another dimension like X, Y, and Z. And we can extrude a certain number of millimeters of filament, just as we're moving generally a different number of millimeters around in space. And as I say, that's a standard format, and you can, if you're feeling brave, edit that around directly or create it directly, though it's much more usual to do it automatically. Okay, fitting 3D printed parts together, and this brings us back to the Minkowski sum. It's often the case that you want to put 3D print parts together, perhaps you want to glue them together or whatever. Now, you might think that on the left there, incidentally, is a 3D printed electric motor, and the radial pieces, the grey and the red ones, are separately printed parts that need to be assembled together. You might think that you just have to subtract those from the central hub and you'd end up with a hole the right shape. Unfortunately, that won't work for the reason I mentioned earlier, namely that the prints tend to be slightly undersized as far as holes are concerned. If you just subtract the shape you want to fit from the shape into which you want it to fit, then you'll find that they don't fit together, they're too tight. So you need to expand the shape a little bit. And to do this, we use a thing called a Minkowski sum, illustrated on the right there. Top right is the Minkowski sum of a square and a disk. The mathematical definition of this is you choose a point on the disk and you allow that point to visit all the uncountably infinite number of points in the square, and you take the union of all the infinitely many disks that you've got, and you end up with the rounded cornered shape on the right, which is slightly larger than your original square. Now, that's not the way it's computed, but that's the mathematical definition of it. But you can take the Minkowski sum of any shapes. So, for example, if we take the square, we can add that sort of stabby, sharp shape to it, and we end up with the thing on the right there. Now, some CAD systems can do this, notably FreeCAD can, because FreeCAD incorporates OpenSCAD, which has a Minkowski sum operation. So if we take the object that we wanted to make a hole for, and we add a little disk to it, bottom left there, tiny little disk, we end up with a slightly larger object, which we can subtract from the central hub and thereby give us something that will fit together. And the general rule here, because this is quite computationally intensive to work this this Minkowski sum out, is to keep the added shape as simple as possible. You might think you always wanted to add a sphere, but the trouble with a sphere is that a sphere consists of lots of triangles, many more, for example, than a number of triangles needed to represent a cylinder. And as a consequence of that, a sphere is more difficult to add than a cylinder. So keep the added shape as simple as possible. Okay, post-processing 3D prints, we can paint them. We can paint them with paints. We can paint them with resins. This is slightly dangerous, so be very careful if you do this. You can take a 3D print and you can put it in a solvent vapor. You've got an organic solvent that's a solvent for the 3D print material. You suspend the print above it and you warm up the solvent, and the vapor causes the surface of the 3D print to dissolve very slightly, and surface tension then smooths it off. Obviously dangerous. First of all, you don't want to be breathing in solvents, and secondly, you're heating an inflammable material, which, as I say, is obviously dangerous and to be treated with extreme caution, but this is something that's sometimes done. We can electroplate prints. If we take a 3D print and cover it in electrically conducting paint, we can then electroplate onto it to form a much thicker layer of, for example, copper, as is illustrated here. And finally, fixings. Often when you've got a 3D print, you need to screw it to other things. We can use screws, rivets, and all sorts of other ways to fix these things together. Top left is some brass parts riveted onto a 3D print. Top screwing a screw into a 3D print. You don't need to have a thread in your 3D print to do this. If the screw is going to be a steel or brass screw, you can just use the thread on the screw itself to cut its own thread in the 3D print. If you make the hole slightly undersized, that works fine. Or you can get these little inserts, which are threaded inserts, which you can insert with a heated soldering iron into holes in 3D print, and then you've got, for example, a brass insert that's threaded. Finally, using the trick which I did with the magnets, you can leave cavities in your 3D print and drop nuts into them, into the print, in order to have a solid steel nut inside a 3D print, which you can use to then attach it to something else. And you can either have those accessible when the print's finished, or you can have them embedded so that they're never seen again. Okay, Ohad, over to you.
Yes, so I'm going to share.
Okay, I'll stop sharing.
Okay, so Adrian, thank you so much. And I think that it's a privilege to work with you. There was a question about what's the difference between subtractive and cutting. So sheet lamination, this process is actually working on cutting layers of sheet and glue them into each other, creating a three-dimensional model. The ASTM and the ISO define 7 categories of 3D printing. We've been in material extrusion, like we just learned about material extrusion. Let's move to wet polymerization. So everything that Adrian was talking about was about thermoplastic, which is actually plastics that when you heat them, they deform and you can create whatever you want with them. An interesting part of that you can reuse them. You can reheat them and use them. Thermoset, it's a different process of polymer. You need an actually chemical reaction in order for them to be hardened. So you start with a liquid, and then most 3D printing processes using photopolymer that you use a UV light to harden those materials. So let's talk about the first 3D printer technology that we know of, stereolithography. So what we have over here, we have a laser that goes, and actually this is not the correct diagram. The model is supposed to be like on bed. So the tray, this is our tray, is like it goes up in a layer height, and then the laser is hardening the liquid by like pointing a UV light in the right in the right range for this specific material. And each time the model is going to go up, and then we are going to have another layer to be printed by that. There are, let's say, in the vat polymerization, there are mainly 3 different technologies. One is SLA as we know it, which is working with a laser. So each place that it's going to harden, it's a laser point. It's actually a vector printing. And then we moved to DLP, which is using a projector. So a projector is going to project the layer each time. And that means that instead of moving to a contour and then the infill of that, you can project the entire layer instantly, meaning that the printing is going to be faster. But remember, a projector is a pixel base. So instead of having like vector printing, if you go back to our previous weeks, now we talk about pixel, or actually voxel, which is the 3-dimensional pixel. And MSLA, which is now more common, it's actually an LCD screen that being on the bottom of the tray, and each time project a different layer. So again, it's going to be pixelized. This is why if we look at those technologies, SLA is going to be more precise, but slower than the other technologies. Using resin for 3D printing, you need to take some protection before that. So in order for the polymerization place, there might be lots of smell in the room and other. Remember that the resin itself is not a plastic, it's not hardened yet. So you need to take care of yourself and wear gloves. Better to have like a mask as well. And in many cases, you need to have a UV glasses. After we print, the part itself can be deformed because it's not fully cured yet. So you need to be very gentle with the part. Usually at that stage, we are going to remove the support, and then we are going to put it in a bath of IPA. It's better to use an ultrasonic wash for that, but in many places we don't have an ultrasonic, so we're going to put it in the bath, and we might shake the bath a bit. Then it depends with the material, but some materials ask us to wash it after with water. Some of them just say that let's dry the IPA in air, and then you're going to put it in a UV cure chamber. Now the UV cure chamber, this process is very toxic. This is why it's recommended to have a BUFA or a good ventilation when you do that.
Ohad, there's 5 minutes left, and I need a minute at the end.
Okay, so I will be fast. So usually when we print with that polymerization, we're going to put the part in 30 degrees. The reason is because we are using liquid. So we want the liquid to go out and drain out of our model, and as well because it's going to get because of the movement, it's going to get stuck to the tray itself if we are not going to do the 30 or 45 degrees angle. What we wanted, so with SLA and those technologies, you're going to have a finer details, a higher accuracy. You're going to use a mono material, which now Adrian showed you that with FDM we can have a multi-material. There is a lot of post-processing after. So sometimes we think that this technology is faster, but actually the post-processing takes more time, and it's non-recyclable part. I will be very fast with a multi-material printing. So multi-jet printing, you have a multi-heads that prints like an inkjet that drops off a material. And then usually you are going to have a roller that is going to flatten them. So you're going to get those voxels. The idea of that technology that it's cure at the parts, the material when it falls down because due to the UV lamps, and you can use multi-material as part of that. So your print can have multicolor or multi-material behavior. A project that we've done, we asked engineers if you have bins of 50% rigid material and 50% flexible material, how would that behave? And when we put gravity on that, we show that because of the way you're going to populate the part in itself, they are going to behave completely different. And that if we go to Lockheed or other companies, they are using this as impact absorption or other research. So it's not only how you look at your model from outside, it's how the model is behaving from inside. If we go to medical, the capability of having a range of different behaviors allow us to mimic medical and help us help doctors to practice before their surgery. We had a surgery that the doctor came to me and told me that there is a child with a heart defect and the surgery is going to take more than 60 hours and most likely she is going to die. After we send them plenty of hearts of this child that we printed mimic completely, he practiced and the surgery took 15 hours and she survived. So this is like what you can do by mimicking behaviors. I will not talk about lab on a chip, but the fine details that you can do now allows us to move beyond what we expect before. My recommendation about everything that the different technologies is this book. We put a link for that book. It covers like most of 3D printing technologies, showing you showcases and as well what can be done and what's recommended to use which technology. So let's move to our assignment. You have a group assignment. Adrian showed you lots of rulers of how we use them in order to make sure that our printer prints well. As well, in many cases, you need to know your printer before you print in order to understand what can you do. And some printers they have different kind of wall thickness that they can do and different kind of behavior. So this is the first thing as part of our assignment. And the main assignment is design a 3D printed object that could not be made subtractively. Now, I know that you didn't do subtractive yet, but you need to think about what are the advantages of additive manufacturing that Adrian just, we discussed about them, about how can you enclose parts within parts and make them move, or do like models that cannot be done, cannot be made in a different way. And I will show some examples. Per Fab Academy, like we always need to make sure that we are not using we are not taking the storage of the Fab Academy. You have this chart. 3MF is now the most recommended file format I can recommend you because it's more compressed and it allows you to do like texture and multi-material, and also for some printers within the 3MF itself, you can put the toolpath itself. So the G code can be embedded within the 3MF.
Yeah, Ohad, we're at 12 o'clock.
Okay, so we are going, I wanted to show, this is the book, just a minute. Okay, I think that this page is one of the most interesting students that have done things in the previous years. This is from 2003 from the VACH. And what she's done, she printed model and she's doing a post process of heating the model and then inflate it and deflate it. So you can see that like what she wanted to try to check if the model is watertight after she printed, and this is like an interesting project. This project, I think that it's part of Neil's. Yes, it's part of Neil's course. So they took Chinese balls, which is like you have a ball within a ball within a ball, and created a very interesting
that one is notable
design.
because the web page is the design tool. He just wrote code to make the STL. Okay, and then very
But what
quickly,
also he's talking about the post-processing that completely destroyed part of the model. So this is like something that you need to take into consideration, that also when you remove the support within any of the technologies, you need to think of that before you design it. So orientation is important. Yes.
We're over time. Very quickly show Valdemar. Yeah, so this was a student in the early days of AI who, instead of he designed it, he asked AI designed a surreal vase and submitted that for the homework. And that counts as design as long as you document the workflow. But this was using a Stratasys multi-material printer. This was an extreme form of something that you couldn't easily make subtractively with an AI design workflow.
And maybe I'm just going to put that. Okay, it doesn't work, but.
Okay, so in the last minutes, scan anything. And as a note, there are a lot of, linked on the class page are a lot of good photogrammetry apps that work on cell phones. These are rapidly maturing. Extra credit, you can print the object you scanned, which can be non-trivial. Then the heart is the design task of something not made subtractively. Global open time for any challenge of any kind. And then Monday is a really good group for an AI recitation. And with that, thank you so much, Adrian and Ohad. It was a pleasure to listen to you. So great job, and look forward. This is one of the more creative weeks. I look forward to seeing what all you come up with next week.
As do I. I think.
Good.
Everybody. Bye.
Bye-bye.
Bye-bye.
Thank you. Bye.
Bye.
Thank you. Bye-bye.
Bye.
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 Adios.
Adios.